All right, so this is a statement just to understand the concept of resistance. Once again, when the electrons are flowing through the conductor, these electrons can collide with the ions of the metal. And these collisions make it more difficult for the current, more difficult for the charges to flow, and that causes the opposition, that causes the resistance. So this is the definition to understand the resistance. But if you have to write in the exam the definition of resistance, then you write it the ratio of voltage to current. All right, generally they ask you for 1 mark, define resistance. So you can write it, define it mathematically in terms of its expression, or descriptively you can say ratio of voltage to current. All right, so on this phrase we'll be having a detailed discussion when we'll be studying Ohm's law in the upcoming pages. Now, formula. From this very statement we can get to the formula of resistance as well, which in that case would be voltage over current. And the resistance, the physical quantity resistance, is represented by the symbol capital R. Right, so R equals to resistance equals to voltage divided by current. All right, and on the right side we are writing symbolically R equals to V over I. Or sometimes you can also write R equals to P dot D over I, potential difference over current. And make sure that when you're finding the resistance mathematically, the voltage should be in volts and the current should be in amperes, because if there are prefixes there, then your answer would not be in the in ohms, it would be with the prefix. The unit of the resistance. All right, so we can obtain the unit from the formula itself. Like we know, resistance equals voltage over current. Now let us write the units of both of them. I mean, the unit of voltage, as we know, is volts, and the unit of current is ampere. So the unit of resistance would be volt per ampere, or VA minus 1, power minus 1, because ampere was in denominator. Now the same thing, volt per ampere, can also be written as ohm, 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 which is represented by a symbol omega. All right, just like the unit of work done. All right, if we recall the formula of work done equals to F into D, then in order to find out the unit of work done, the force is measured in newtons and the displacement is measured in meters. So the unit of work done is Newton meters, which can be written as, and is generally written as, joules. And joules is represented by capital J. Likewise is the case, volt per ampere is written as ohm, and then ohm is represented by the symbol omega. Then this is what a resistor looks like, and this one. But in the circuits, when you have to draw this resistor, you draw this one, the rectangular block. So this is the circuit symbol as per the specification of 4-level physics. All right, I mean 90% of the time we use a different symbol of resistors generally, which is something like this. But for our physics syllabus, we use the symbol of resistor as a rectangular block. Now, like I said, resistance means the opposition to the flow of current. So if there is high resistance in a circuit, that would imply that there's more opposition to the flow of charges. Hence, it would be less current. So if there's more opposition, there would be less current. And if in a circuit there's less resistance, that implies there's less opposition. Hence, if the opposition is less, more current can pass through the circuit. All right, so now we have two circuits and we'll try to calculate mathematically the value of resistance in these two circuits. So for example, in the first one we have a battery of 9 volts. This one battery is of 9 volts, and the other one in the second circuit we have the same battery which is of 9 volts. That's the EMF of the battery. All right, and then in the first one circuit we used an ammeter. This one, an ammeter, like I said, is a tool that is used to measure the amount of current to the circuit. All right, the convention is you should be connecting it on the with the positive terminal of the battery. That's the convention. But anyway, since ammeter does not give you the direction of the current unless you have a digital one. On the digital one you can get a negative sign. So let's say the amount of current that we measured through the ammeter was 2 amperes. 2 amperes in the first one circuit connected to a 9 volt battery, and in the second one circuit we got the amount of current as 1.5 amperes. Now this is a resistor, but we don't know the value of that resistor. We don't know how many ohms that resistor is, and this is what we need to find out, and we have to find it out mathematically. Now, first of all, we have to write down the formula that resistance equals to voltage divided by current. The voltage or the EMF or the potential difference. In circuits, we don't differentiate between them. Is 9 volts divided by the amount of current, which is 2 amperes, and that would be 9 divided by 2, 4.5, followed by the unit ohms. So the resistance in the first circuit is 4.5 ohm, right? Now let's calculate for the second one. R equals, we use the same formula, V divided by I, and that would be 9 volt from the battery divided by 1.5 amperes, and that'll be 6 ohm. And that makes sense. In the second circuit you were having less amount of current, and that's precisely because the resistance in the second circuit was more. That's why you were having less amount of current. So if you know the amount of current flowing through the circuit, you can always comment about the resistance, or you can compare the resistance of the two circuits if you know the potential difference and you know the amount of current passing through both of them. So here's an analogy, since we have studied 3 things now. We studied resistance, we studied potential difference, and we studied current. So think about it, the water pump that has to pump the water is like the voltage. It has to supply the energy. How much energy is being supplied? That's the voltage. and the water that is flowing through the pipes is the amount of current. Now this current has to do some work. It has to turn, like in this case, the water has to turn the water wheel. So it has to do some work. There's an opposition to the flow of water. In the analogy of the circuit, that would be your resistance. So the water pump providing the energy would correspond to the battery providing the electrical energy. The water in on the right side would correspond to the current in the circuit, and the water wheel that is consuming the energy, or that needs the energy, or that is opposition to the flow of water, corresponds to the resistance or to the load or to the fan on the left side. And there's another analogy. So voltage is like someone that is pushing, that is forcing, that is providing energy to the current. So this is your ampere. Ampere means this is the amount of the current. And resistance is something which is opposing the flow of those charges, the flow of current. So resist the voltage being supplied by the battery or being supplied by the power source is driving the current, is providing energy to the current, and the resistance in the circuit is opposing the current. So this is very beautiful and very smart analogy over here. Let us solve some of the sample questions. Here we have another case. A diagram shows a resistor connected in a circuit. The current in the circuit shown in the ammeter is 2 amperes. And the voltage across the resistor is 15 volts. Calculate the resistance of the resistor. So you need to score the marks. So first of all, you write down the formula. And you get independent marks for writing down the formula even if there's some mistake in the calculation. Then you write down R equals V. The value of potential difference across the resistor is 15 volts divided by the current passing through the circuit is 2 amperes, 2 amps. And that gives us 7.5 ohm, 7.5 ohm. This is the amount of resistance in the circuit. And if you connect the ammeter in this case, positive with the positive terminal of the battery, ammeter has two terminals, a red terminal and a black one. So the convention is you connect the red terminal, which is a positive of the ammeter, with the positive terminal of the battery, and the reading it would give, if it is a digital ammeter, the reading would be positive. And if you connect it the other way around, the amount of current would be same. It would still give you 2 amperes but with the negative sign. So in this one we don't really bother with the direction. You can connect it anywhere around, the amount of current would be same. All right, so measuring the resistance. So this is a new learning objective that is added in our syllabus for 2023 to 2025 exam. A very simple case. Matter of fact, we have solved plenty of questions regarding this one. All we have to do is to construct a circuit through which we use ammeter and voltmeter to measure current and voltage separately. Then we can apply the formula, which is resistance equals to voltage over current. So all you have to do is to construct a circuit here. So it would pretty much looks like this one. So all I can do is just copy paste this one. Copy that one, and I'm going to paste that one over here in the box. So this is the circuit that you need for the measurement of resistance, for the calculation of resistance experimentally. All right, so In this case, I'm going to remove all the values because in different cases the values might be different, and let's just skip the values from for now. That's not given, that's not given. All right, so whatever the value of current and the value of voltage you get from there, you apply this one formula, R equals to V over I. And then you hit on the calculator and then you get the value of resistance in ohms. So this is how we can find the amount of resistance in a circuit. All right, so the next thing that we have is the factors that affect the resistance of a wire or the resistance of a conductor. And the very first one is length of the wire or length of that conductor. Now, for a wire of uniform cross-sectional area, that means the thickness of the wire is kept constant. That is the controlled variable. We're not changing it. We are comparing the lengths only. The resistance is proportional to the length of the wire. It means the longer the wire, the more the resistance or the higher the resistance. And the answer is once again in the understanding of resistance. Resistance is due to the collision of the electrons with the ions of the metal. And if the wire is longer, more number of collisions occur while the electrons travel from one end of the wire to the other one. And hence, more the number of collisions, there would be more resistance. So the longer the wire, we can write here, the further the electrons have to travel, the more they are likely to collide with the metal ions. And the greater the resistance. All right, for this one, I was saying if the length of the wire increases, the resistance also increases. And the increase in resistance is proportional to the increase in the length. Or I should say the change in resistance is proportional to the change in length. If you decrease the length, then the resistance would also decrease. Now, one of the analogies you can think about it as you're driving a car on a road. Then as you have to, let's say you have to start from here and your journey ends at this point over here. Now, throughout the track, your car would be facing some of the obstacles. There would be hindrance, there would be opposition by some other vehicles that would be there on the road. So for your vehicle, there would be some other automobiles, there would be some other vehicles that you need to pass through. So that is the opposition. But if you have to, let's say, start from here and you have to cover a lot of distance, the length of your track has increased a lot. In that case, there would be generally more opposition. There would be more number of vehicles that you need that would be opposing you. So the longer the road, the more the number of vehicles, and there would be more opposition. All right, so the next thing, the cross-sectional area of the conductor or the thickness of the conductor, like how thick the conductor or the wire is. That would also affect the amount of resistance that it has. So for a fixed length, if we're not changing the length, we're not changing anything else, we're not changing the temperature, then its resistance is inversely proportional to cross-sectional area. It's the other way around with respect to the length. So inversely proportional to the cross-sectional area. Reason: the greater the cross-sectional area of the wire, the more electrons are available to carry charge. The more electrons are available to carry charge along the wire length, and so lower resistance. So if the cross-sectional area of the wire increases, the resistance of the wire decreases. So the thicker the wire, the less would be the resistance. And mathematically, this can be written as resistance is inversely proportional to cross-sectional area. Now, you can think about it in this way. All right, this is not the analogy that explains the principle or the reason for increasing the thickness, and the result of that is decrease in the resistance. But you can think about it in a way that if you have to go through a broad road, a wide road, it'll be easy for you. There will be less opposition, there would be less resistance for you. You have to go from a wide path, there is less resistance because there will be a lot of room. If you have to go from a narrow path, if you have to go from a less wide road, let's say from a very narrow road, there'll be a lot of obstacles, there'll be a lot of resistance because you'll be bumping into pretty much everything because there's a lack of room. So this is the analogy that you can keep in your mind, just to explain, just to memorize the relation between cross-sectional area and the resistance. Moving on to the next one. In this case, in the third case, we're not changing the dimensions of the wire, we're not changing the dimensions of the conductor. Rather, we are going to change the temperature of the wire or the temperature of the conductor. So it turns out that the temperature of the conductor also varies the resistance, also determines the resistance. For all the conductors, I repeat, only for conductors, as the temperature increases, the resistance also increases. And this is for conductors only. All right. So reason once again in the understanding of resistance, that as the temperature increases, the vibrations of the atoms increase. The vibration of the atoms increase, and the electrons collide more frequently. Electrons collide more frequently with the metal ions and lose energy more frequently. So hence the flow of electrons drop. The flow of electrons drop. All right. Now it must be kept in mind that this is the relation only for conductors. Matter of fact, I should highlight it over here because the wires I've written for metallic wires, wires are mainly made up of conductors. Because in the wires, we design the wires from such a material that transfers maximum amount of current. But for some of the materials like silicon and germanium, which are semiconductors, the temperature increases, then the resistance would decrease. So for semiconductors such as silicon and germanium, it is the other way around. You increase the temperature, the resistance drops. All right. Then the other thing is the material of the conductor or the material of the wire also determines the resistance, right? So for example, you have let's assume you have two wires or two metal bars. First one is 1 meter long, the other one is 1 meter long. First one is, let's say, having a cross-sectional area of 1 centimeter square. The other one is also having cross-sectional area of 1 centimeter square. First is kept at a room temperature 25 degrees Celsius. The other one is also kept at the same temperature 25 degrees Celsius. First is the first wire is made up of let's say copper, and the other wire, let's say we have made a strip that is made up of plastic, right? Now both of these strips or both of these materials have the same length, they have the same uh, cross sectional area. Even if I make this one, let's assume that this is also a metal, silver, or let's make it more dramatic, this is gold. This is wire that is made up of gold or a strip. Even if they have same length, they have same cross sectional area, they are kept at the same temperature, still the resistance offered by both of them would be different, because not only resistance depend on the dimensions or the temperature, it also depends on what the object is made from, or what's the electronic configuration of that material, or what is it made up of. So for instance, gold is such a good conductor, its resistance is much less compared to copper. So resistance depend on material of the wire as well. Material of the wire or the conductor or the substance. Copper is a good conductor and is used for making wires. All right. Now, resistance itself is not a good or a bad thing. Sometimes we need some of the instruments in which we have to use high resistance or substances with high resistance, and sometimes we need to use for some of the objects we need materials with low resistance. If we have to make the wires, we generally use make it of copper, which is having comparatively less resistance. It's not lesser than gold, but it would be too expensive. We have to keep a check on the price, we have to keep a check on the cost as well. So copper is like a good bargain at the price, with the price as well. We have to keep a lid on the price. Nichrome has more resistance and therefore it is used in heating elements, because the more the resistance, more energy would be wasted in the form of heat. But if you're making something in which we need heat, for example heater, that heat is not counted as wasted because we need heat energy from it. So heating elements of electric heater. Then we have some of the sample questions here. Which factors would both increase the resistance of the wire in a circuit? So let's start off with the first one, size of the wire and temperature of the wire. If I increase the longer, means it has more length. If I increase the length of the wire, the resistance does increase, but lowering the temperature, the resistance does not increase. Shorter wire, resistance decreases, so that can't be the case. Thicker wire, the resistance decreases for the thicker wire, because you have for thicker wire, you can think about it, you have a broad or a wide road and you can travel easily without much opposition. For a thinner wire, the narrow road, the resistance would increase, and for the high temperature, the resistance would increase. So D is the right answer for this one. Then we have the next one. A metal wire has a resistance L and cross-sectional area A. What is the resistance proportional to? We studied that resistance is directly proportional to L and it is inversely proportional to cross-sectional area. Now we can combine these two things and we can write them as resistance is proportional to L over A. Collectively, you can say resistance is directly proportional to L over A, but if you want to read it as resistance is directly proportional to length and inversely proportional to cross-sectional area, if you want to read it separately. So in A-level physics, we break down this expression as well, and we introduce the concept of resistivity and the effect of resistivity on the resistance. But here, we just need to consider these two things and the material of the wire. So resistance is proportional to L in the numerator, because with the length it is directly proportional, and with the cross-sectional area it is inversely proportional. All right, here we have the next one. PQ and R are electric symbols. What do these symbols represent? Now these symbols should be done the smart way. First of all, let's say you have not memorized or somehow you fail to recall all of these symbols, but you should be doing it in a smart way. For example, this one we are pretty sure at this stage that this is a symbol that represents resistance. So let's look for the option in which R represents resistance. First one R represents relay coil, third one R represents fuse, fourth one R represents relay coil. So B has to be the right answer, because B is the only option in which R is representing resistance or resistor. So it can be done in a smart way even if you don't know the symbols for the other ones. Moving on to the next one. Here we have a length of the resistance wire is used as a resistor in a circuit. All right, so we're using a wire as a resistor in a circuit to control the amount of current. Probably 4 separate changes are made to the wire, which change will not reduce the value of the resistance of the wire. All right, let's start with the bottom one, D. Its temperature is decreased. So we have to reduce the value of resistance. In order to reduce the value of resistance, if we decrease the temperature, the resistance would decrease, and that would change the resistance. That would reduce the resistance. So we have to look for the change that will not reduce. So D can't be the right answer. If we decrease the length, if you have to travel for a short distance, you'll be probably facing less obstacles, you'll be facing less resistance. So C can't be the right one. B, its cross-sectional area is increased. You're passing through a wide road, you'll be probably facing less obstacles, you'll be having less resistance. So B can't be the right answer. A, it is covered in an insulating sleeve. Now this is the right answer. You can do it by the process of elimination as well. So if you cover that in an insulating sleeve, that is not going to change the resistance of the wire itself, because you have not changed the dimension. We didn't study any case, any factor in which resistance is being affected by the insulating sleeve. All right. So